55 hours, 54 minutes, and 53 seconds after leaving Earth, a master alarm sounded inside a spacecraft 200,000 miles from home. Main bus B voltage collapsed. A dull, metallic bang traveled through the hull. Oxygen pressure in Tank 2 read 0. Tank 1 was bleeding into vacuum. Through the small window, a silver mist of escaping gas curled out and vanished into the black. NASA has sold this moment for 56 years as the beginning of the emergency. It was not the beginning. It was the moment the emergency became impossible to ignore any longer. The tank had been screaming for 13 days. Nobody was listening in the right frequency. The onboard tape recorded a low-frequency rumble roughly 1.4 seconds before the bang. The explosion itself was not the underlying failure. It was the final audible confession of a slower failure that had already been happening for weeks. This is what the celebration buried. The public remembers Apollo 13 as a rescue story. The internal record describes something closer to a delayed detonation with a paper trail. The most famous line from the mission is misquoted. Jack Swigert said, "Houston, we've had a problem." Past tense. Already happened. If the sentence was rewritten in cultural memory, ask what else was. Wherever you are watching from, whatever time it is where you are, hold one question in your mind. What were you taught about Apollo 13 in school? A near miss? A triumph? A movie? Because the tape tells a different story, and the tape is still archived at Johnson Space Center. The tank did not fail suddenly, it failed terminally. 3 weeks before launch, during a countdown demonstration test, oxygen tank 2 refused to empty. Engineers activated the internal heaters to boil off the remaining oxygen. The thermostats were rated for 28 volts. The ground support equipment ran at 65 volts. The thermostats welded shut on the first surge and stayed shut. The heaters ran for 8 hours. Temperature inside the tank reached an estimated 1,000 degrees Fahrenheit. The Teflon insulation on the fan wires melted. Nobody knew. The temperature gauge on the ground console only read up to 80 degrees. The gauge that was supposed to catch the problem was blind to the problem by a factor of 12. The tank was refilled. It was cleared. It flew. 5 compounding failures produced the bang. Inadequate specifications, an operational error, a manufacturing shortcut, a testing procedure that damaged the hardware, a design that could not detect the damage. Not bad luck. A system. The tank was manufactured in 1966. By the time it reached the launch pad, it had been dropped, miswired, overheated, and cleared for flight. The story of how that happened is the story NASA did not tell. The official story goes like this. A routine lunar mission suffered an unexpected explosion. 3 astronauts and a brilliant ground team improvised their way home. Everyone survived. NASA called it a successful failure, and the phrase stuck. It became the title of Jim Lovell's memoir. It became the spine of a Ron Howard film that grossed over $300 million. It became the way an entire generation learned to think about the mission. The problem is not that the story is false. The problem is that the story is edited. Look at what was said publicly in the first 72 hours after splashdown. NASA administrators emphasized the crew's professionalism, the flight controllers' ingenuity, the resilience of the hardware. What they did not emphasize was the pre-flight de-tanking incident. That was buried in Appendix F of the Courtright Commission report, read by almost nobody outside the aerospace community. The public got the movie. The engineers got the paperwork. Here is the reframe. The phrase "successful failure" sounds like humility. It is not. It is strategic language. It concedes that something went wrong while insisting that the response redeems the event. That framing served two purposes. It protected the remaining Apollo missions from cancellation, and it protected the agency from the harder public conversation about how a tank cleared for flight could reach the launch pad with melted insulation inside it. The Courtright Commission's public language was tempered. Its findings were not. The internal chain of causation identified inadequate specifications, an operational error at Kennedy Space Center, a manufacturing shortcut at Beech Aircraft, a testing procedure that damaged the hardware, and a design that could not detect the damage. Read those 5 phrases in sequence. They do not describe an accident. They describe a process. Each step was survivable in isolation. The system that allowed all 5 to compound without any single engineer being empowered to stop the flight. That system is what the phrase "successful failure" was designed to protect from scrutiny. The film added another layer of softening. It compressed the timeline. It personalized the danger. But it erased the boil-off, the voltage mismatch, the drop damage. The mechanism disappeared, and only the drama remained. Ask most people what caused the Apollo 13 explosion, and they will say a tank blew up. That is not an answer. That is the absence of one. The crew themselves became the emotional shield for the institutional story. Their courage was real. Their competence was real. But their survival was placed at the center of the narrative in a way that made asking harder questions feel disloyal. Celebrating them made critiquing the system that endangered them feel like ingratitude. To understand why the tank failed, we have to go back 4 years to a shelf in a California factory. Picture a metal sphere about 26 inches across. Inside it, oxygen is stored not as a gas and not quite as a liquid. It sits in a state called supercritical, held at roughly 900 pounds per square inch and cooled to about -297 degrees Fahrenheit. At that pressure and that temperature, the distinction between liquid and gas dissolves. The oxygen behaves like a dense fluid without a surface. It fills every corner of the container uniformly. This is efficient. It stores an enormous amount of breathable and combustible material in a small volume. It is also, by design, a bomb that has not been armed. Pure oxygen is not dangerous the way most people imagine. Oxygen itself does not burn. What it does is make everything else burn faster, hotter, and more completely. In ordinary air, which is about 21% oxygen, a spark on a piece of insulation might smolder briefly and go out. In a pure oxygen environment, at 900 pounds per square inch, that same spark can ignite materials that are considered non-flammable in normal conditions. Aluminum will burn. Stainless steel will burn. Teflon, which is used specifically because it resists heat and chemical attack, will burn if the ignition energy is high enough. Every material inside that tank was chosen with this constraint in mind. Every material was a compromise between the properties it needed to have and the fact that it was surrounded by the most aggressive oxidizer environment engineers could legally build. Now put a fan inside the tank. It has to be there. In supercritical storage, the oxygen tends to stratify. Warmer, less dense regions form near the heaters. Colder, denser regions settle elsewhere. Without mixing, the pressure and quantity readings become unreliable. So a small electric fan stirs the contents periodically. That fan is driven by wires. Those wires pass through the interior of the tank. They are wrapped in Teflon insulation because Teflon is one of the few polymers that can tolerate liquid oxygen without spontaneously reacting. Here is the single point of failure. If the insulation on those wires is intact, the tank functions. If the insulation is damaged, the wires can arc. An arc inside pure oxygen at 900 pounds per square inch is not a spark. It is an ignition source in the most reactive environment a spacecraft carries. The tank was designed with the assumption that the insulation would remain intact. That assumption is the entire safety architecture. Not multiple redundant barriers, not fail-safe isolation, one layer of polymer. That is the reason the tank did not explode on the pad. That is the reason it worked on Apollo 8, 9, 10, 11, and 12. And that is the reason it detonated on Apollo 13, 55 hours into the flight. The insulation did not stay intact. And the reason it did not is documented. In 1965, 5 years before the mission, NASA authorized a routine upgrade at Kennedy Space Center. The ground support equipment used to condition the spacecraft before launch was changed from 28-volt DC to 65-volt DC. Higher voltage meant faster charging and shorter cycle times. The change was documented in an engineering change order and distributed to the relevant subsystems. Most of the affected hardware was updated to match. Almost all of it. The oxygen tank thermostats were not. The thermostats had been specified in 1962 by Beech Aircraft, the subcontractor building the tanks for North American Aviation, which built the command and service module for NASA. The spec called for 28-volt operation because that was the internal spacecraft voltage the tanks would see in flight. The engineers who wrote the spec were not wrong. They were writing for the flight environment. What they did not account for, because they were not asked to, was that the tank would also see ground support voltage on the pad during testing. When the ground voltage doubled in 1965, nobody at Beech was informed that the thermostats now needed to handle 65 volts as well. The change order stopped moving between departments. This is the failure mode that killed Apollo 13. Not a broken part, a broken conversation. There is a term for this in systems engineering. It is called a specification gap. It occurs when a change is made in one part of a system without being propagated to every other part that depends on the original assumption. Specification gaps do not show up in physical inspections. They do not appear on test benches. They only manifest when the two mismatched components are asked to work together in the exact conditions the gap describes. For 5 years, the mismatch sat inside the design documents, dormant. It waited for the countdown demonstration test on March 27, 1970, when the ground team, unable to drain oxygen tank 2 through the normal fill line, decided to boil off the remaining oxygen using the internal heaters powered by 65-volt ground equipment. The thermostat saw 65 volts. Their contacts, designed for 28, arced and welded shut in the first fraction of a second. Once welded, they could not open. The heaters had no thermal cutoff. They kept running for 8 hours. And here is what makes this a paperwork failure rather than a hardware failure. The change order existed. The document existed. The information was inside the NASA system. It simply did not reach the one engineer at Beech Aircraft who could have caught the mismatch. 3 astronauts nearly died because a piece of paper stopped moving. If that could happen to Apollo with its budget and oversight, what does that say about the vehicles being built today on faster timelines by contractors NASA no longer fully controls? If the same tank had exploded on the ground during testing, it would have been a bad day. The pad would have been damaged, the tank would have been replaced, the engineers would have written a report, and the program would have continued. Nobody would have died. This is important because it exposes something about spaceflight that is almost impossible to feel until you sit with it. The failure that killed nobody on the ground nearly killed 3 men in space. Same tank, same mechanism, same physics, different location, different outcome. Distance changes category. That is the rule the intuition keeps refusing to accept. At 200,000 miles from Earth, the crew had no abort mode available to them. The flight had passed the point where an immediate return to Earth trajectory was possible. The only path home was a free return trajectory around the far side of the Moon, using lunar gravity to slingshot the spacecraft back onto an Earth intercept course. That path took 87 hours. 87 hours of powered-down cabin, minimal water, and life support built for 2 men lasting 4 days, now being asked to keep 3 men alive for 4 days on a tighter margin. The abort mode table for lunar missions is not a menu, it is a countdown. In the first minutes after liftoff, an abort meant a splashdown in the Atlantic. Within a few hours, the options narrowed to a return trajectory that took a day. By the time Apollo 13 was 55 hours out, every abort mode except the free return trajectory had expired. Not because of the explosion, because of physics. This is what a scale rupture looks like. On Earth, a fuel cell failure means calling a mechanic. On the moon-bound trajectory, a fuel cell failure means calculating whether the lunar module's ascent engine has enough burn duration to correct the return path without overshooting the atmospheric entry corridor. The corridor is roughly 2 degrees wide. Too shallow, and the spacecraft skips off the atmosphere and returns to interplanetary space with no way back. Too steep, and it burns up. The crew had to hit that corridor after 4 days of degraded navigation, hand-flown course corrections, and a thermal environment cold enough that the guidance computer's alignment drift became a genuine variable. Here is the point most explanations miss. Space missions are not scaled-up airplane flights. They are a different regime. The safety margin that keeps an airliner alive during an engine failure does not exist at lunar distance. There is no diversion airport. There is no glide path. There is only the trajectory you are already on, and whatever you can do to modify it before the consumables run out. And the consumables were running out. The body pays for those 87 hours in ways NASA did not publicize. The cabin temperature inside the lunar module dropped to approximately 38 degrees Fahrenheit. That is 3 degrees above the temperature of a household refrigerator. The crew wore standard flight suits, not thermal gear, because the mission had been designed around a heated command module with a functioning electrical system. Once they shut down the command module to preserve its battery for re-entry, the heaters went with it. Condensation formed on the walls, on the instruments, on the windows. It dripped. It pooled in the corners of the equipment bays. The crew slept in wet suits when they could sleep at all. Water was rationed to 6 ounces per man per day. 6 ounces is less than a coffee cup. It is roughly 1/5 of what a healthy adult needs at rest, and the crew was not at rest. They were flying course corrections, transferring guidance data between 2 spacecraft computers by voice, and monitoring their own life support. By the time the command module splashed down, the 3 men had lost a combined 31.5 pounds. Fred Haise had lost 14 pounds by himself. Haise developed a urinary tract infection during the return. Severe dehydration reduces urine output, allows bacteria to concentrate, and lets a minor infection climb from the bladder into the kidneys. By the time he reached the recovery ship, the infection had progressed. He spent weeks recovering. He never flew in space again. Lovell was reassigned to management. Swigert was pulled from the Apollo-Soyuz roster and later elected to Congress. He died of cancer in 1982. The crew survived. All 3 of them paid. Now factor in the atmosphere they were breathing. Carbon dioxide levels inside the lunar module climbed steadily because the LiOH scrubber cartridges were designed to support 2 people for 2 days, not 3 people for 4 days. Partial pressure of CO2 rose past 10 millimeters of mercury and kept climbing. At 15 millimeters of mercury, cognitive impairment begins. At 20, judgment degrades severely. At 30, unconsciousness follows. The crew was approaching the impairment threshold when the ground team finished designing the improvised adapter that let them use the command module's square cartridges in the lunar module's round receptacles. They call it the mailbox. It was cardboard, plastic bags, duct tape, and a soot hose. It bought them the atmosphere they needed to survive. But think about what the mailbox actually represents. The two spacecraft, both built by the same agency, both flying the same mission, used incompatible CO2 scrubbers. That is not an oversight. That is a design decision made somewhere upstream by someone who did not model the failure case where the crew would need to shelter in one vehicle using the consumables of the other. Which raises a harder question. If ingenuity saved this mission, what does that say about the margins the mission was built on? The mailbox is celebrated as ingenuity.
That framing is not wrong, but it is incomplete. The mailbox was built to solve a problem that a properly designed mission architecture would not have created in the first place. Two spacecraft flying together, sharing crew, sharing consumables, sharing failure risk, using incompatible cartridges for the same critical function. That is a redundancy failure written into the blueprint. Why did it happen? Because the command module and the lunar module were built by different contractors on different schedules with different weight budgets. North American Aviation built the command module. Grumman built the lunar module. Each vehicle was optimized independently. The square LIOH cartridge was designed around the ventilation geometry of the command module. The round cartridge was designed around the tighter volume constraints of a lander that had to reach the surface and take off again. Neither design was wrong on its own terms. The two were never asked to be interoperable, because nobody at the program integration level modeled a scenario in which the crew would spend 87 hours living in the lunar module while the command module sat cold. That is the point. The redundancy did not fail because engineers were careless. It failed because the interfaces between vehicles were treated as separate problems rather than one system. Each contractor built to spec. Each vehicle passed its qualification tests. The gap was in the space between the specs, and no single engineering group owned that space. This pattern is not confined to Apollo. It is structural to how large aerospace programs are managed. Contractors optimize what they are paid to optimize. Interoperability requirements have to be enforced from the top down. And when program managers face schedule pressure, interface requirements are often the first thing that gets softened. The result is a mission architecture that works when everything goes according to plan, and fails in unexpected ways when a single subsystem forces the crew to use the vehicles in a configuration nobody wargamed. Apollo 13 exposed the pattern. The pattern was not fixed, it was patched. The mailbox problem was solved for later missions by pre-stocking universal adapters. That is not the same as solving the underlying issue, which is that mission architecture keeps producing redundancy gaps because the incentives that produce them keep operating. The crew had roughly 6 hours of breathable atmosphere remaining when the mailbox began scrubbing CO2. 6 hours. That is the margin the mission actually had. Not 4 days, not 87 hours. 6 hours between survival and impairment. The rest ran on that margin, plus the improvisation of a ground team that had to invent a solution using only the objects the crew had already carried into space. If the margin was 6 hours, what was the safety architecture of the entire program? To understand why NASA still calls this a win, you have to understand what NASA was fighting for in April 1970. The agency had landed men on the moon 9 months earlier. The Cold War pressure that had funded Apollo was dissolving. Public interest was already declining.
The Nixon administration was quietly looking for places to cut. Apollo 20 had been cancelled 3 months before Apollo 13 launched. Apollo 18 and 19 were on the chopping block. And then, a spacecraft nearly killed its crew on live television. If NASA had presented the accident as a systemic failure caused by paperwork gaps and manufacturing shortcuts, the political damage would have been catastrophic. Instead, the framing that emerged was successful failure, ingenuity under pressure, human resilience. The system worked because the crew and the controllers made it work. All of that is defensible. Some of it is even true. But it also served a specific institutional purpose. It preserved the appearance of competence at exactly the moment when a harder public conversation would have accelerated the program's cancellation. That framing did not prevent cancellation. Apollo 18 and 19 were cancelled anyway in September 1970, 5 months after Apollo 13. What the framing preserved was the agency's credibility for future programs. If Apollo 13 had been remembered as evidence that NASA's quality control system was compromised, the space shuttle would have faced a much harsher congressional review in the mid-1970s. The successful failure framing bought the agency the political space to move on. Compare this to how later disasters were framed. When Challenger exploded in 1986, the immediate messaging emphasized heroism and sacrifice. The Rogers Commission then did the hard work of identifying the O-ring problem, the management failures at Morton Thiokol, and the launch decision made against engineering advice. The public got the harder story eventually, but only because the deaths made softening impossible.
Columbia in 2003 followed a similar pattern. The Columbia Accident Investigation Board explicitly criticized NASA's culture, its normalization of deviance, its willingness to fly with known anomalies. That report exists because 7 astronauts died. Apollo 13 did not produce a comparable public reckoning because the crew survived. Their survival made the softer framing possible. And the softer framing meant the deeper lessons about interface management and specification propagation were absorbed narrowly by the engineers who worked the problem rather than broadly by the institutional culture. This matters now because that culture is being replaced. NASA no longer runs its own crewed vehicles. Boeing builds Starliner, SpaceX builds Crew Dragon. Both operate with less internal quality control than Apollo had because the government-contractor relationship has shifted from oversight to purchase. The FAA reviews launches for public safety, not vehicle integrity. And now, in 2026, private companies are building the vehicles that will carry the next crews back to the moon. Read the NASA Office of Inspector General report released on June 30, 2026. Then, read the Courtright Commission's 1970 findings on Apollo 13. Then, compare the language. The 2026 report on Boeing's Starliner crew flight test identifies 3 primary causes. NASA's hands-off contract approach limited insight into Starliner's development. Boeing's inadequate systems engineering created reliance on subcontractors without sufficient oversight. The commercial crew program's culture prioritized provider success over technical rigor. Those are 3 separate paraphrases of the same failure mode that killed Apollo 13's oxygen tank in 1970. Specification propagation broken between prime and subcontractor. Interface requirements softened under schedule pressure. Institutional incentives that reward launching over questioning. The Starliner mission that carried Butch Wilmore and Sonny Williams to the International Space Station in June 2024 was originally planned as an 8 to 14-day flight. It became a 93-day stay after 5 thrusters on the service module failed during rendezvous, forcing Wilmore to manually pilot the docking. The 2 astronauts were eventually brought home on a SpaceX Dragon capsule in March 2025. In February 2026, NASA retroactively reclassified the mission as a Type A mishap. That is the agency's most severe failure category, typically reserved for missions involving loss of vehicle or life. It took NASA 21 months to apply that label. The Aerospace Safety Advisory Panel called that delay concerning. As of March 2026, the helium leaks and propulsion system failures that caused the crisis remained unresolved. Artemis II flew on April 1, 2026, and returned safely on April 10th. The crew went around the moon and back. That is a genuine achievement. It is also the case that they flew with a heat shield known to be defective. The avcoat material used on Artemis I had cracked and shed chunks during re-entry in 2022 because gases inside it could not escape. NASA identified the root cause. It designed a new heat shield for future missions, but the Artemis II shield was already installed. Replacing it would have delayed the flight by 18 months. So NASA flew the compromised shield and modified the re-entry trajectory to reduce heating instead. Analysis and testing supported the decision. Independent experts continued to object. The crew survived. This is the pattern. Solve the specific problem. Do not solve the system that produced it. Fly the compromised hardware with a workaround. Cite testing and analysis. When the workaround succeeds, cite the success as evidence the process worked. When it fails, invoke ingenuity, resilience, lessons learned. The Apollo 13 oxygen tank was cleared for flight in 1970 through the same reasoning. Testing supported the decision. Analysis supported the decision. The workaround failed anyway because the failure mode was not in the tested envelope. It was in the paperwork. We solved the specific tank. We did not solve the system that produced the tank. Return to the moment. 55 hours, 54 minutes, and 53 seconds after launch. The tape is still archived at Johnson Space Center. You can request it. What it recorded in the 1.4 seconds before the bang is not strange. It sounds strange only because we were taught to expect silence there. The rumble is the sound of pressure escaping through a fractured wire jacket. The chirp in the telemetry is the fan motor's electrical signature shifting as its bearings feed voltage into oxygen that is no longer separated from the arc. The tank was talking. It had been talking for 8 hours on a Kennedy Space Center test stand 3 weeks earlier, when its thermostats welded shut. It had been talking for 2 years in an engineering change order that stopped moving between departments. It had been talking since 1966, when it was manufactured to a specification that assumed a voltage the ground equipment no longer supplied. The strongest proofs are on the table now. The voltage mismatch, the 8-hour boil-off, the paperwork gap between Beech Aircraft and Kennedy Space Center. The CO2 scrubber incompatibility between 2 vehicles built by the same agency for the same mission. The political framing that turned a systemic failure into a celebration of ingenuity. And the pattern repeating in 2026 in the Starliner mishap report and the Artemis II heat shield decision. Let me be clear about what this video is not saying. It is not saying that Apollo was wasted. It is not saying the engineers were negligent. It is not saying the crew's survival was undeserved. It is not saying that human spaceflight should stop. Jim Lovell, Jack Swigert, and Fred Haise were extraordinary, and the ground team that brought them home did work that deserves every hour of celebration it has received. What this video is saying is smaller and harder. The physical reality of what happened to Apollo 13 is more serious than the cultural memory of what happened. The difference matters Because we are building the next generation of crewed vehicles under similar pressures, with similar contracting structures, on similar schedules, and the failure modes are structurally identical. Successful failure is a phrase that lets us stop looking, and we cannot afford to stop looking. There is a narrow hope. NASA's internal culture did change after Apollo 13. The Courtright Commission's real findings did reshape how the agency thought about system safety for the shuttle era. Change is possible when the harder version of the story is told. Whether it happens again depends on whether we remember Apollo 13 correctly, or the way we have been told to. The tape is still archived at Johnson Space Center. You can request it. The sound is still there. It has been there for 56 years. It is still telling us the same thing.